Welcome to the fourth exercise for lecture Pattern Recognition and Machine Learning. In this exercise, we focus on codebook training. For this, we will first review what codebooks actually are before we then look at the two training algorithms that you saw in the lecture. Then we will have two comprehension questions and we will finish with a Python demo. So let's go ahead and let's get started. Before we discuss codebooks, we first need to discuss the feature space. And for this example here, for this introduction, I want to just look at a very simple two-dimensional feature space. So on the first axis, we can symbolize here in my plot our first dimension in the feature space, or my first feature, x0. And then on a second axis, I have x1 as my second feature or second feature dimension. And those two features I can combine in the vector x of n, and meaning that I can at different times have different vectors, and I combine those two elements x0 and x1 into this vector x, and this is then called the feature vector, combining features x0 and x1. And I can generalize that a little bit more. I can actually say that in such a vector x, I don't just have two elements, but I have m elements in there, because I can have a feature space with 3, 4, 5 dimensions or features. So in this vector is contained x0 of n up to xm minus 1 of n. And then m is the number of feature dimensions. And in this feature space here, m equals 2 in a two-dimensional feature space, I can have different observations of features. I can, for example, observe this point here. Let's just call it x of 0, so our very first feature vector. And then we can have x1 right here. We can have here x2, up here x3, x4, and x5. And this is just some example I created so we can move forward in a review of our codebooks. But before we do that, I just want to finish up the definition of the feature space here. We saw that we have different observations of features, and we can put all those feature vectors together in a matrix capital X. And then in this matrix, I have all the feature vectors starting from n equals 0 up to n minus 1. So X is then our feature matrix, and n is the number of feature vectors, or in some cases n, capital N, is called the number of observations, the number of times that I obtain a feature vector from observing some kind of event. And as you know, a codebook is supposed to represent a number of vectors, here in our case feature vectors. It's supposed to represent those feature vectors by a smaller number of codebook vectors. So let's say if I wanted to draw some probable codebook vectors in here, I could say, okay, I could represent those 3 feature vectors down here by 1 codebook vector, and those 2 up here, they seem like a group. I have a codebook vector up there, and over here this seems off, so I just put a codebook vector right onto that feature vector. So I basically have represented those 5 feature vectors by 3 codebook vectors. And just like my feature vectors, I can name my codebook vectors as well. Then name them C. And this one down here is C0, up here it's C1 and C2. And similar to our X, I can define this vector then Ci by having its elements Ci of 0 and Ci of 1. So Ci is our codebook vector. And if I want to generalize this as well regarding dimensions, I can say that in this vector I have the elements Ci of 0 up to Ci of m minus 1. And those codebook vectors I can put into a matrix as well. This is my matrix C, and it contains all my Ci's. So C0 up to ck-1, because I can have a different number of copebook vectors than I can have feature vectors. So C is then my copebook matrix. I put the matrix in parentheses here because sometimes C is just called the copebook. And then K is the number of copebook vectors. To see whether one copebook vector represents one individual feature vector well, we can look at a distance, and here we're looking at a very simple distance definition. This definition can be done in different ways, but here we're looking at a very simple geometric version. And this distance, we call it d of x of n and ci, and it is a distance between those two vectors. And basically how we define it, it's just the difference vector of those two vectors and then the norm of that, and we take the squared number 2 norm, so it's the squared Euclidean norm. And this is the very simple definition. Some ways how you can take it further is to introduce a limitation to this distance function, because we will be using this distance function in our cost function later, so that it might make sense to limit this distance when we have very large or very small numbers involved, when we, for example, look at logarithmic features. And if you have some importance to certain features, or it's uncertain whether you have obtained them with the right precision, you can introduce an element-wise weighting. So the distance, it doesn't have to be the simple Euclidean norm of the distance vector, but you can add some more things on top there. And with this distance, we now have a rating for how well one individual copebook vector performs for one feature vector. So with this, we can now obtain a measure, or the cost function, for how well the overall copebook works. So we use this distance function, so this d of x of n and ci. And here we look at the minimum of that, and the minimum over I. So when we look at one feature vector, we look at all the copebook vectors, and we look, okay, which one represents that feature vector the best, so which one has the minimum distance, and we take that value. Here in our example, let me mark in blue all the distances that we're looking at. So we just look at maybe x1, and we have the distances between C0, C1, and C2. And you can clearly see that basically the shortest arrow is the one here that I'm marking green, between x1 and C0. So this value of the distance function would then be the result of this minimum operator. And for our cost function, we want to look at this minimum value for each feature vector, and we sum those values. So in the sum, we go, of course, then from n equals 0 up to n minus 1. And if we then normalize the sum by 1 divided by n, we get the average minimum distance that our copebook produces for all the feature vectors that we have available. So d bar is then our cost function, or you can simply call it the mean distance. And this function we want to minimize when we try to obtain our copebook. So keep this in mind. Here, I'll mark it for you. This is the very important cost function that we want to use now when we go into the copebook training. And in copebook training, we try to find that copebook C, where the number of copebook vectors k is usually smaller, or actually a lot smaller than the number of feature vectors that we have available. And we want that copebook to represent our big matrix X, so all our feature vectors. And that is best according to the cost function d bar that we defined above. And we do this by iterative algorithms. you learned too in the lecture, we have the k-means algorithm and the LBG algorithm. And what they effectively do is, first of all, minimize or at least decrease the cost function that we have. And they actually perform a unsupervised clustering. And this was it then for the just basic review of codebooks, and we can go into the two algorithms, the k-means and the LBG algorithm. So let's move to the next page. Here we keep the basic example of the feature space with x0 and x1. And we'll look at k-means and LBG, and we'll do this in a very basic, rough form so that you get the basic idea. And this is not a very mathematical view, although I will use some formula there to underline what is happening. But if you wanted to put it all in formula, then this is not the place where you will find everything in order. But let's start with the k-means algorithm. Every algorithm, it needs an initialization. So we start with an initialization, and we do this by choosing k arbitrary vectors, and k, it has to be set. This is the number of codebook vectors we want to obtain, and we choose k arbitrary vectors from our matrix X, and those are then our initial codebook, and we refer to our codebook as CP, and P is then basically the iteration number in our algorithm, and here at the beginning it's basically just 0. So if I want to choose, let's say 3, because we had 3 codebook vectors on the other page as well, so let's choose 3 feature vectors as codebook vectors. So let's choose x0, x2, and x5. This is then just our initialization. And then once we have initialized, our second step is always the classification. In the classification, we find the minimum distance for each feature vector, and by finding the minimum distance, we also find the corresponding codebook vector that is responsible for that minimum distance. And then in return, if we say basically in a list for each codebook vector, which feature vectors basically belong to that codebook vector based on that minimum distance measure, we can group basically our feature vectors. And because we have 3 codebook vectors, we then have 3 feature groups. On the right here, I have one codebook vector right on x5, so that is one group. There's no other feature vector in there because it's so far out. Then the other group belongs to the codebook vector down on the bottom, so that one x0 and x1 are closest, and to the codebook vector above that, x2, x3, and x4 are closest. So the classification groups I have now marked in green circles. After the classification, we move on to the correction. And this is actually where we obtain a new version of our codebook. So we go from CP to CP plus 1. And how do we do this correction? We have obtained those feature groups, and those feature groups we use to update our codebook vector. And it's basically just the average of those feature vectors, and this average replaces the old codebook vector entry. The new resulting codebook entries I will now mark as green X's in our graph on the left. So when I look at the feature group on the right with just x5, the codebook vector was already on that feature vector, so the average of x5 is x5, so that one stays there. But at the bottom with x0 and x1, there the average is just in the middle of those feature vectors, so the codebook vector actually moves to the right. And for the other group, for x2, x3, x4, the average of those 3 vectors is up here, so we move more to the top and more towards x3 and x4. Once this correction is done, we move on to step 4, which is the termination of the algorithm. Or to be more precise, we have termination conditions, and we check whether those conditions are met and whether we should terminate right here after this iteration. But if those termination conditions they're not met, we go into another iteration of the algorithm. So we move back to step 2 and we do step 2 and 3 and then end up again in step 4 termination. But let's run it through one more time. So if I want to now do the classification in blue here, I have to again group my feature vectors to the copub vectors. Again with x5 it's still that very same feature vector. And then down here now something new happens. Now additionally to x0 and x1 in that group there is x2. All those three they belong to the very bottom green cross, and then to the top green cross only x3 and x4 belong. And then if I want to do the corrections, so I want to go from green crosses to blue crosses, so I do the average again. Here with x5 it's still my copub vector. Then in the group of x3 and x4, that average is then just in the middle of those two, so the copub vector moves even more to the top. And then our group with x0, x1 and x2, there I have now one copub vector more in the middle. And here you see then that this basically is the codebook that I drew on the previous page, which was sort of intuitive if you wanted to cluster those feature vectors. And now it would actually be likely that our termination conditions, which we will talk about later, would be met and that we would abort this algorithm. So let us move on to the LBG algorithm. Here this algorithm, it has a different initialization. We actually initialize a C of k and p, which is the mean over all training vectors. So this is just one vector because we are at k equals 1, and because we initialize, we are at p equals 0. And as you will soon see, we have two iteration variables here. We have our vector, our copub vector size k, and the actual iteration where we then use also the k-means algorithm for that copub size. So we have k and p as our top indices there. And once we have initialized our codebook, we increase k, so we go from, for example, 1 to 2. We can do this by splitting, so we can add and subtract small numbers to our vector elements. And this then gives us two copub vectors. And with this two copub vectors, or whatever the number of copub vectors then is, I can run the k-means algorithm, and I actually initialize the k-means algorithm with that codebook that I currently have after the increase of k. So I initialize with c of k and 0. And then once I have run a full run through of the k-means algorithm, which terminated by the k-means abortion criteria, I go into the termination of the LBG algorithm, or again, I check for the conditions. And if those are not met, I also go back to step 2 and 3 here, which is then increasing k, so our codebook size. And just formally, I want to then reset p, because I will then run the k-means algorithm from the beginning with this new initialization of my new grown codebook. And this is repeated until I terminate. So the LBG algorithm, it basically runs the k-means algorithm, but it starts with a small codebook, and then after each k-means run through, it increases the codebook size. This completes our review section, and I would like to move on to the comprehension question section, where in the first question I actually want to talk about the abortion criteria that I just mentioned here on the previous page. So let's first talk about the k-means abortion criteria, and there is actually three main ones, so A, B, and C. The very first abortion criterion is basically a cost function threshold. So you remember we have our average minimum distance, and I can say, okay, so for me it's enough if I reach a certain value of that cost function and then I can stop. I don't need to optimize more, and this is the abortion criterion you want to use or set to your liking. Then B, this is a convergence criterion, or you can also see it as a stability criterion. So we check the cost function of two consecutive iterations, and by looking at the ratio of those values and by comparing that ratio to 1 minus epsilon, which is a very small number, we actually check two things. We check that our cost function is not getting larger over our iterations, so it's sort of a stability criterion. And we check for convergence, so we're not getting larger in our cost function, but if our improvements are just so very, very small, we can say we've more or less converged and there's no point in continuing on in doing the k-means algorithm, so we can abort. And then the last option of abortion is very, very simple. Basically, if neither A or B holds, then we have to abort at some point. So we usually set a maximum number of iterations that we will perform. So those are then the abortion criteria for the k-means algorithm. So let's look at the LBG algorithm, and you see here that I've titled the criteria there D and E, and this is because we actually adopt the k-means abortion criteria because we use them in the LBG algorithm, but of course the entire LBG algorithm, it will abort by D and E. And criterion D is that we look at the codebook size as an abortion criterion. So you remember that we increase the codebook size in every LBG iteration, and if we say, okay, for example, codebook size of 10 is large enough for us, or it's after that it's getting too large for our purpose, so at k greater than 10, abort the LBG algorithm. And E is then also a convergence or also a performance gain criterion. And here we usually look at the elbow curve, which I have plotted down here, which is from the lecture. And we want to see there if splitting the codebook vectors and increasing our codebook size, whether it improved our performance much, or if we should go for a smaller codebook so we could be more efficient later on when applying it. We want to compare the cost functions at the end of the k-means run through for each codebook size. So we look at those values here, and we want to compare the neighboring values there and see what's the difference in dB, how much did I gain from increasing the codebook size. And there you can also set a threshold and say, okay, if I don't gain enough there, then I will abort, and you can either keep that codebook size, or you can actually then go back to the smaller codebook. So these are all the abortion criteria for both k-means and the LBG algorithm. The second question is, how are codebooks used for piecewise affine linear mapping? And I first want to motivate using such a mapping. Here we see a graph from the lecture, and we see that we have two input features, and they're clustered in some way, but it doesn't really matter. It's that we go from those two feature values from a two-dimensional vector space to one, so we have generally a mapping. But we don't actually have to go to a scalar. We can go to a vector, generally a mapping, but it's nonlinear here. And then whenever we have such a mapping and we need to perform it, compute it in some way for whatever reason, One problem usually is that you just don't have that nonlinear function. It's not directly available and you have to estimate it in some way, and it's computationally easy to estimate using linear mapping. And then the second thing is, even if you had this nonlinear function during runtime, if it's a mapping that you have to perform often, it's actually probably not that computationally efficient to perform this mapping all the time. It's more efficient to actually use linear matrix operations. And if you can then have such a linear mapping which is for your purpose close enough to the nonlinear function, then this is how you should do it. So let's look at the method of the linear mapping. We want to go from our feature vector, or generally a vector x of n, and we want to transform it to a different vector generally. Here in the picture it's a scalar, but we can go to a vector, and this is then y of n. And we perform this transformation by subtracting a vector m of x from x. Then we multiply this difference vector by a matrix M, and the result of that, we can add a bias term, which is again a vector my. To actually get a good performance out of our mapping, we can't estimate this entire nonlinear function just using this one mapping. So the idea is to do a piecewise approximation of the nonlinear function. And for our formula up there, that means that we have to add piece indices to our quantities. So we add I of n to m, we add it to mx, and we add it to my. For our example function, this means that we can have individual mapping functions for different areas in our two-dimensional space, as you can see down here. And then you can also see here how we actually find out which function we have to apply whenever we have a feature vector. And we do this by a codebook search. And the codebook search gives us back the index of the codebook. And this is basically the index that we're using here up there in our mapping function. So an approach for the generation of such a mapping is, whenever you have lots of data, you first do a codebook training to find your clusters, and then for each cluster you train or estimate those individual mapping functions. And then when you have new data, you can do your codebook search and you have your estimated function ready to apply to your feature data. Now let us move on to the Python demo. We have one demo where we just look at basic properties of codebooks with a already implemented k-means algorithm from a Python library. And then in the second part, you will actually implement some lines of a k-means and of the LBG algorithm to then use it and to see how the algorithms behave. For both our demos, we will be working with some artificial data. And we're actually drawing those data points from Gaussian distributions. So here I specified 4 different means and 4 different standard deviations, and those pairs, they define then one Gaussian. And we're working with a 2-dimensional feature space. So I can create those points by running the make blobs function with the centers and the cluster standard deviations. And then if I plot this, you see here that we have a bunch of data. I've color coded them based on what center and standard deviation pair the data points come from. And you can certainly see here that we have Gaussian shapes for different Gaussian shapes. And you can also see that especially for example, the brown one here has a low standard deviation, the purple one, it has a high standard deviation, and we also have some overlapping points. So it would say that the Gaussians, they sort of do overlap. So later on, when we look at the properties of the k-means algorithm, this will be important. So we can now go ahead and on this data set run the k-means algorithm. This is then an algorithm that's already been, or a version of the algorithm that's already been implemented in a Python library. And we can run it with 4 clusters because we have 4 clusters in the input data, but actually the k-means algorithm, it does not get this data separately. So this algorithm will get all the data points together, so all of them. So when we run them and we plot the results, you can see the our codebook entries here in bright red, and you can see that this, yes, it does represent our data set well, but interesting to see is that it represents the overall data set well. It might not represent the individual Gaussians well. So you see here that we're not hitting with our red point the center of the blue Gaussian here. So that when I go down here in my classification section, which basically means now I want to see and plot which points belong to which codebook entry, then you can see here and that this area here, it's all purple, but you have to remember we can't compare those colors directly in the 2 pictures because we're working with an unsupervised method and I have no influence on the order of how the centers are estimated. So we can't compare colors here, but we can compare the areas of where the points are. So if we now compare the purple points here, I should compare them to the blue ones up here, and you can see there that they're not all identical. So it's been shifted a little bit down here to the right. And if I want to say that those 2 Gaussians, there were different classes, then my class distinction line would be here, whereas it should actually be up here. But of course, we're not really doing classification here, but I just wanted to make you aware of that. It's an unsupervised method, and I can't really estimate the individual Gaussians here with the centers, but it's about the overall data set, and based on that data set, we're getting our codebook vectors. Of course, I can now also increase the number of clusters I want to have, and then I get some more points down here, and I can then of course do some more classification, and you see how which points are then matched with which codebook vector. Okay, you can go ahead and play around a little bit with the parameterization. You can also change the data set up there again, and just play around a little bit. But we will now move on to the next demo where we will actually look at the k-means and the Albert-Jean algorithm a little bit more in detail. Here in this demo, we're actually working then with the same data set. So I've already created this here for you so that you see that it's the same data set. And then in this section, we first have some helper functions, because we want to implement the k-means algorithm and the Albert-Jean algorithm. And I thought it would be useful to first implement some helper functions because we need some basic operations for our algorithms. And the first basic operation is that we need to compute the value of our distance function. And the function we have here does this for one feature vector against all current codebook vectors. So we go in with a feature vector 1 by m and our cluster matrix k by m, and we should get a vector with all the distances, it's 1 by k. And then of course we also want to find the minimum distance, and we go into this function with the same as for distance function, and we call of course then a distance function, but we need to do something else to then find the minimum. So this function should return the minimum value. And then when we want to actually know but which codebook vector produced the minimum value, then we need the argmin distance. So this should be computed here. And here, this last helper function is then the actual cost function of our entire codebook. So this should, with our entire feature matrix. Before it was called X, so it's a matrix n by m, and we have our codebook vectors, our capital C, it's k by m. When we have this as input, we should get one value out, which is just the cost function of our current codebook. So these are then our helper functions. And you have a section here where I've created a sample for you, and I've printed for you what the expected output is. So when you run those functions that you've then completed yourself, you should see exactly that output. If you don't, then you've done something wrong, or at least not in the way that I intended the functions to work. Okay, then the next section is actually the k-means algorithm, and I call this k-means custom because we already used the k-means algorithm in the previous demo where it was already implemented from the library. And here we give the k-means algorithm our feature samples. We say how many clusters we want, what our maximum number of iterations is, and we can actually specify initialization for our codebook, but we don't have to. And at the beginning, we just set some thresholds for abortion. Then here we do some data set splitting into test and training. We do some sanity checks. And then the first real operation is that we initialize actually our codebook. And this can either be done by copying the initialization matrix that was specified by the function call into our clusters, or you do something else, something that we discussed in lecture. So you should complete this here. Then it's just some allocation. And down here is the actual iterations of the algorithm. So we iterate over our maximum number of iterations. And we can, of course, abort earlier, so we have some abortion criteria down here. And in here is actually where our classification and correction takes place. And here I want you to specify what our actually correction should be. We do some checking here as well, so you could think about why we have to do this. It's more of a sanity check for our implementation. So I want you to find out those correction values or the new codebook. And I also want you to think about when we abort earlier than our max iterations, what would then actually be the return values of this function. So you need to fill this in here as well. Then you can apply the k-means algorithm, and you can play around here as well, like we did in the previous demo. And maybe you see some differences to the k-means algorithm we used earlier. And we do the classification again, and then we have the LBG algorithm. And the LBG algorithm, it will use the k-means algorithm that we've implemented. And here we have then as parameters for a function next to the samples, we have how many times we'll split. So we're implementing here really a split of each codebook vector. So we're always doubling in each iteration. We also have a maximum number of iterations. And when we talk about the elbow curve, we had that minimum split gain. So you can specify this here as well. And what I want you to do is implement the initialization of our codebook. And then here in where we actually do our iteration, I want you to actually do the splitting of the codebook vectors, because the actual updates, they're going to be done by our k-means algorithm, so there's not that much to be done here, but you should implement one version of how to increase the number of codebook vectors. I've actually increased it here for you, but you might need to make them unique so that you don't have twice as many codebook vectors, but I mean, they're not unique. You always have two of the same. So fill something in here. Okay, and then you can also apply this algorithm, and you will also see some output. I printed a bunch of info here there, so you can compare then what the algorithms do, and it will give you some info about our abortion criteria and how are we doing. But this is then all you need to know really about what we're going to do here, and I will now implement those question marks that I showed you, and we will run and discuss the individual sections. First of all, I want to say that the way I implement everything coming now is just one version, and it's not always the easiest or not always the most efficient way, but actually when we're doing similar things, I always try to show you different versions of how you can actually implement something so you get a better idea of what we're actually doing content-wise, to have different perspectives. So keep that in mind when we now go through the next sections. So let's start with the distance function. Here we go in with one feature vector and with our codebook matrix. And we want to have, if we have k codebook entries, we want to have k distant values coming out of there. And I want to perform this as a matrix sort of operation. So what I first do is actually to repeat the sample that I have. So I do this by NumPy's repmat, and I repeat it as many times as I have clusters. And once I have done this, I can then, between those two matrices, simply compute a distance matrix, which is the difference matrix. And on this matrix, and I can then just compute the Euclidean norm, and I square it here because we want the squared Euclidean norm. And again, this is not the most efficient way, but just to show you what we're doing there. So we can go ahead and run this. Then with the next one, we want the minimum value of that vector. So basically the return value should just be minimum of dist. And when we want the index of our codebook vector, which produces the minimum value, then here it's NumPy's argmin of dist. So that's it there. So we can run those two. And then here, when we want to compute the cost function, we need to compute the minimum distance for each feature vector. So we call in our own function minDistance, and we iterate over our feature vectors. And of course we have classes as input, and then we get a vector of minimum distances. And then our cost function return value should then be the mean of that vector. So NumPy's mean of that dist vector. And when we run this function and then run our value check that I have given you, you see here that I have the values printed there in the comments. So you should have those values as well. Now let's go to the initialization of the k-means algorithm. What we want to do here is we want to select arbitrary vectors from the feature vectors and set them as our codebook vectors. So we need to somehow find those arbitrary vectors. And how I want to do is I want to draw k random vector indices from the feature vector matrix. So I do this using the UDEL's random sample without replacement, where n population is basically the number range that I have available. So this is the number of training vectors, and then n samples is how many vectors I want to select. So that's the number of clusters. So this then gives me back integer values, which I can use then for indexing my training feature vector, and just by indexing select the submatrix that is my cluster initialization. Now let us compute the codebook update. So we compute the candidates of our new codebook vectors. And you know, a new codebook vector, it's actually the mean over the feature vectors that have been classified as belonging to that old codebook vector. So we have to, of course, call on NumPy's mean function, and then we have to select the right vectors from samples train. And how do we do this? So we did the classification up above, and the classification result is in classvec. And we say that when we iterate over our codebook vectors, then if classvec equals our iteration index, then we want to select that vector for our codebook vector update. So let's look at the abortion criteria. The first abortion criterion is that we abort to achieving our distance threshold. And this means that, well, we're still improving, but we have achieved an accuracy that is sufficient for the application target. So we can just return the clusters we currently have, and we can return the current cost function. Now, in the other case, when we check for our, we check the distance of the last iteration with the distance that we have now, and compare that to a threshold, we check for different things. Once we check for convergence, yes, but this can also mean that we check for stability. And if you want to throw them all together in one pot, then actually this update is not really a good update. So we might consider actually throwing away this update and returning the previous clusters and then the previous distance function. But this depends, of course, on how you interpret this abortion criterion. Okay, but this then completes the k-means algorithm. Now, when we run it, we see some info about the internal values of the algorithm. So you see here the cost function improvement and why we abort. And here we aborted because we reached the maximum number of iterations. And we've also plotted again where the clusters are. So the estimated codebook vectors or the chosen codebook vectors. And you can see here that those are not the ones that we obtained in the earlier demo. And when I run these several times again, you'll see that at some point we actually will get those vectors. And yeah, I just wanted to make you aware that our implementation is not deterministic, because our initialization is different in every run. So what codebook vectors we actually get from our k-means algorithm, it does depend on how we initialize the algorithm. So sometimes it might actually make sense to, I mean, this is regarding every machine learning pattern recognition algorithm. You might want to run it several times and have a different metric to evaluate the runs against each other, because initialization, it does have a huge role in the actual outcome and performance. And regarding performance, we can briefly look at the classification plot where we don't see anything new there, so we can just go ahead and move on to the LBG algorithm. The initialization of the LBG algorithm is simply the mean over all feature vectors. We do have to be careful here though, because for Python and NumPy and how we've written it, we need to cast the mean value actually to a NumPy array. Okay, then I wanted you to compute actually the splitting of our codebook vectors. So we do this by actually duplicating all the vectors and then to one vector adding an offset and then to another vector subtracting an offset. And here, because of the way that I've duplicated the vectors, I have to select the second vector in this way, where I want to then subtract the offset. And then we have to, of course, find the offset. So we do this in the randomized manner. And there's several ways, options to do this. This is just one arbitrary method for selecting the random value. And I do this by calling on NumPy's uniform function. And I wanted to bring even some more chance into this by also making the sign of the offset random. Now we're able to run the algorithm and actually also do our clustering. And as you see here, we again have some output, but we have the output that we saw before from the k-means algorithm and some additional output. So we repeat the k-means algorithm several times for different code sizes, and then we have different output there. And when we look here then at the plot, this just looks like we had performed the k-means algorithm with k equals 4, so with 4 clusters. And I want to end my demonstration here, but I would very much encourage you to, especially with the LBG algorithm, play around with the parameters, with the thresholds, and just to make yourself familiar with how those algorithms behave. That concludes this exercise video. Thank you for watching.